The graveyard just sent something back. For decades, the Kuiper Belt was a smear on the edge of our solar system. It was too dim, too distant, too cold to read. We knew it was there. We knew it was enormous. We assumed it was relatively simple, ancient frozen rubble, the leftover material from a planet that never quite assembled. Then James Webb pointed its infrared eye past Neptune, and the first detailed chemical survey of the belt came back. It did not return simple. It returned with 3 completely different kinds of worlds, and a 4th category that matches none of them, and a question that does not close easily. Why are they still sorted? Before Webb, studying Kuiper Belt objects was a matter of catching faint light. Ground-based telescopes could measure color, roughly reddish or grayish, or somewhere in between. A few spacecraft had flown past individual objects, New Horizons through the Pluto system in 2015, then past the snowman-shaped contact binary Icarus in 2019. Those were single snapshots, each one a glimpse at a specific object for a specific window of hours. They told us a great deal about those individual worlds. They told us almost nothing about the belt as a system. That changed when Webb came online. The DISCO TNO's program, discovering the surface composition of trans-Neptunian objects, was designed to do something no telescope had done before. Systematically read the chemical fingerprints of Kuiper Belt objects across a full infrared range, out to 5.3 micrometers. In that range, ices and complex organics leave unmistakable absorption features, like barcodes. Webb's NIRSpec instrument can read those barcodes on objects billions of kilometers away. The program surveyed roughly 54 to 100 medium-sized objects, not the giants, not the dwarfs, but the intermediate population that makes up the bulk of the belt. The results were published in Nature Astronomy in late 2024 by Noemi Pinilla-Alonso and colleagues at the Florida Space Institute. What they found was not a uniform population. It was 3. The researchers identified 3 distinct compositional groups, and they are as different from each other as chalk and charcoal. The first group, called the bowl type, is dominated by water ice. The second group, the double dip, is rich in carbon dioxide and carbon monoxide. The third group, the cliff type, is defined by complex organics and methanol, 3 chemically distinct populations, cleanly separated, each with its own spectral signature. When you look at the belt from Webb's perspective, it does not look like one place. It looks like 3 places that happen to occupy the same orbital region. The first explanation is obvious. Of course, the belt is not uniform. These objects formed at different distances from the Sun, in different temperature zones. The further out you formed, the more water ice you retained. Closer in, relatively speaking, the chemistry shifts. Distance from the Sun governs what freezes and what evaporates. The 3 groups, on this reading, are simply snapshots of the solar nebula's chemical gradient. The belt recorded where each object was born. That is science working exactly as it should. That should have closed the case, but it did not. Because here is the detail that matters, and it is not a subtle one. Over the past 4.5 billion years, the outer solar system has been through violent upheaval. Neptune did not always orbit where it does now. It migrated outward, dragging, scattering, and reshuffling enormous populations of small bodies in its wake. That migration is one of the central facts of planetary science. Models of it, including the Grand Tack and Nice models, predict that the Kuiper Belt should have been thoroughly stirred. Objects from the inner formation zone should be sitting next to objects from the outer zone. The gradient should be blurred, not destroyed entirely, but significantly smeared. It is not smeared, it is clean. 3 independent clustering methods were applied to the DISCO TNOS dataset. All 3 returned the same 3 groups: The boundaries between the populations are real and sharp. The cliff-type objects, associated with closer-in formation zones, are concentrated among the cold classical Kuiper Belt objects, the objects Neptune disturbed the least. The bowl types sit in their own dynamical niche. The double-dip objects maintain their own coherent chemical character across different subpopulations. Whatever Neptune did to the belt, it did not erase this structure. The simple answer tells you where the groups came from. It does not tell you why they are still this distinct after 4.5 billion years of dynamical churning. Something preserved this. The question is, what? There are a few ways to read this. 1. Neptune's migration was simply less thorough than the models assume. The mixing happened, but not to the degree the simulations predicted. The residual sorting is just a faint echo of the original gradient. This version has the advantage of not requiring anything exotic. It says the models are roughly right, but perhaps calibrated a little too aggressively. The sorting is not a mystery, it says. It is just a survival rate. But the survival rate is very high. Suspiciously high, some researchers think. The groups are coherent across different dynamical populations. Cold classicals and scattered disk objects, objects with very different orbital histories, still cluster into the same compositional types. If the mixing was just somewhat incomplete, you would expect the coherence to degrade across dynamical classes. It does not degrade much. That is the weak point of the first version. The second reading pushes harder. It says the cleanliness of the three groups implies that the primordial sorting was not only preserved, it was actively maintained, or the mixing was far more inefficient than any current model accounts for. The outer solar system, on this view, is more primordial than we thought, not just somewhat preserved, essentially preserved. That distinction matters enormously. If the belt's structure is a near-intact record of the original solar nebula, then the Kuiper Belt is not just a graveyard, it is an archive. The three groups are not just interesting chemistry. They are the original ingredient list of the solar system, written in ice and organics, filed in the cold, and apparently untouched. And then the second twist arrived. A complementary Webb program, led by Joshua MIRI at Northern Arizona University, published in the journal Icarus in 2024, looked not at the medium-sized Kuiper Belt objects, but at three of the larger dwarf planets, Sedna, Gonggong, and Quaoar. These are not tiny objects. They are spherical, large enough to have undergone internal geological evolution, and they sit on very different orbits. Quaoar stays within the main belt. Gonggong reaches further. Sedna, the strange one, has an orbit so elongated that it spends most of its time outside the Sun's heliosphere entirely, beyond the bubble of solar wind, in the borderland of interstellar space. MIRI's team read their chemical fingerprints with Webb's NIRSpec instrument. They found ethane on all three bodies, a hydrocarbon produced when methane is bombarded by radiation over geological time. Sedna showed the most. Gonggong showed less. Quaoar showed the least. The abundance tracks the orbit. The further from the Sun, the colder, the slower the chemistry. And yet, the more ethane accumulates, because Sedna spends more time exposed to the cosmic radiation environment beyond the heliosphere. That alone was striking, but the deeper finding was structural. The spectra of Sedna, Gonggong, and Quaoar do not match any of the three medium KBO groups identified by DISCO TNOS. Not the bowl, not the double dip, not the cliff. They are a fourth category. The largest objects in the Kuiper Belt are also the most chemically isolated. The dwarf planets form their own class, separate from everything below them in size, as if the bodies that grew large enough to potentially melt and differentiate their interiors ended up in a compositional category no smaller object can reach. The belt is not one thing. It is not three things. It is at least four things. And the largest category is the one that fits least neatly into the existing picture. That is where Chapter 1 closes, not on a resolution, but on a gap. The chemistry is strange. The sorting is stranger. The dwarf planets are strangest of all. But the chemistry is not the most unsettling part of what Webb returned. There is a different finding buried in the data that changes the shape of this story in a way that the three groups alone do not. It involves something that was expected to be there, something that models of the outer solar system have assumed for decades. It is not there, and its absence is not a measurement error. It is a finding. Phyllosilicates are not glamorous minerals. They do not have dramatic names. They do not appear in science headlines very often, but they matter enormously because they only form one way. When liquid water reacts with rock over time, phyllosilicates are what you get. They are the chemical fingerprint of water-rock interaction. Find them on a surface, and you know that object was once warm enough, at some point in its history, for water to exist in liquid form and chemically alter the rock it touched. Planetary scientists expected to find them in the Kuiper Belt. The assumption was reasonable. The belt's larger objects were thought to have experienced early internal heating from the decay of radioactive isotopes trapped inside them when they formed. That heat, the models said, should have been enough to melt some of the ice in their interiors, even briefly. Liquid water would have touched rock. Phyllosilicates would have formed. The chemical record of that process should still be sitting on the surface today, mixed in with the ice and organics. Webb's MIRI instrument looked for them. MIRI, the mid-infrared instrument, operates at wavelengths that make phyllosilicates unmistakable. The absorption features are distinct. There is no ambiguity in the reading. The reading came back empty. Not trace amounts, not ambiguous signals, nothing. Across the Kuiper Belt population surveyed by the James Webb Space Telescope, the refractory component, the rocky material, is totally anhydrous, bone dry in the chemical sense, no phyllosilicates, no sign of water-altered minerals anywhere. The result was reported by Vernazza and colleagues in 2025, and it stands in direct conflict with what the standard formation models predicted should be there. Stop for a moment with what that means. The same water-rock chemistry that produced phyllosilicates is also the chemistry that generates amino acids, the molecular building blocks of proteins, in certain classes of meteorites that have fallen to Earth. Those meteorites, carbonaceous chondrites, carry the chemical record of early water-rock interaction in the inner solar system. Scientists have long wondered whether the outer solar system, the Kuiper Belt in particular, was a source of similar chemistry, whether comets and Kuiper Belt objects delivered water-altered, organically enriched material to the inner planets during the early bombardment period. Whether some fraction of the chemistry that eventually led to life on Earth had its origins out past Neptune. The absence of phyllosilicates does not rule that pathway out entirely. The surface is not necessarily the interior. Irradiation processes and billions of years of space weathering can reprocess a surface. What sits on the outside of a Kuiper Belt object today may not perfectly reflect what happened inside it 4 billion years ago. That caveat is real, and it matters, but the absence is still a finding. The surfaces of these objects carry no record of water-rock interaction. If that chemistry happened, it left no fingerprint that Webb can currently detect on the outside. The chemical record that was assumed to be there, the record that connected the outer solar system to the story of life's ingredients arriving at Earth, is missing from the one view we finally have. The simple answer says this is a preservation problem. The real answer may be more fundamental. These objects may never have been warm enough inside, for long enough, for that chemistry to happen at the scale the models assumed. If so, The outer solar system's contribution to Earth's early chemistry is a more open question than it was before Webb. The absence of water chemistry is not an empty result. It is a finding. Now hold that against the belt's larger structure, because the third surprise is not chemical. It is geographical. New Horizons launched in 2006 and reached Pluto in 2015. After Pluto, it continued outward, past the snowman-shaped contact binary Arrokoth at 43 astronomical units, 43 times the distance from Earth to the Sun. After Arrokoth, the science team expected the spacecraft to be moving through emptier space. The Kuiper Belt was understood to have an outer edge somewhere around 50 to 55 astronomical units. Beyond that, the thinking went, there was a gap, then the scattered disk, and then, far further out, the hypothetical Oort cloud. New Horizons carries a student dust counter, an instrument designed to measure tiny particle impacts as the spacecraft moves through space. As New Horizons moved past 50 astronomical units, past 55 astronomical units, past 60 astronomical units, the impact rate did not drop the way it should have if the belt had truly ended. The dust was still there, not at the same density as closer in, but present, still registering, still accumulating. Dust. Dust does not persist indefinitely in space. It is destroyed by solar radiation pressure. Dust at 60 astronomical units has a finite lifetime. For it to still be there, something has to be continuously producing it. Collisions between objects, small impacts, surface erosion. The ongoing presence of dust implies an ongoing population of objects generating that dust. A survey using the Subaru Telescope in Hawaii confirmed what the dust counter suggested. Searching along New Horizons' trajectory, the survey found Kuiper Belt objects at distances out to roughly 90 astronomical units from the Sun. Not a handful, a population. Objects that, by the standard definition, should not be there, past the belt's supposed outer edge, sitting in the gap that models said was mostly empty. Light takes about 8 minutes to travel from the Sun to Earth. At 30 astronomical units, Neptune's distance and the belt's inner edge, that travel time becomes 4 hours. At 90 astronomical units, it is 12.5 hours. These objects are so far that sunlight reaching them left Earth before most people sat down to breakfast, and it arrives at those surfaces near midnight. In that darkness, in that cold, in that silence, an entire population of icy bodies has been sitting, unknown, for 4.5 billion years. The graveyard is bigger than the grave. If the outer edge of the Kuiper Belt extends to 90 astronomical units, or further, then the volume of the outer solar system that we thought we understood is a fraction of what actually exists. The maps we drew were maps of what we could see. What we could not see may be vast. And here is where the story takes its last turn. In August 2025, a paper by Siraj, Kaiba, and Tremaine was published in the monthly notices of the Royal Astronomical Society. The authors measured the mean plane of the outer Kuiper Belt, the average orbital plane of the distant trans-Neptunian objects. In a solar system shaped only by the known planets, that mean plane should align closely with the invariable plane, the weighted average of all planetary orbits. It should be nearly flat, nearly predictable. It is tilted. The mean plane of the outer belt deviates from what the known planets can account for. The deviation is consistent with an unseen body. The paper refers to it as Planet Y, with a mass of at least 1.5 to 3 Earth masses, orbiting somewhere in the outer solar system at a distance the surveys have not yet reached. Be careful here, because the caution notes in this story are real ones. Planet Y is not confirmed. The result rests on 46 non-resonant trans-Neptunian objects. a sample that some researchers consider too small to bear that weight. Observational selection bias remains a legitimate concern. The tilt may have an explanation that does not require an unseen planet. Other researchers, working from different data sets, are not yet persuaded. But the tilt is measured, the measurement is published, and the tilt requires an explanation. Whether that explanation is Planet Y, or some artifact of how the surveys were conducted, or something else the models have not yet accounted for, the tilt does not simply disappear because it is inconvenient. This is what Webb has walked us into. Not a mystery invented for dramatic effect. A real one, assembled from peer-reviewed data across multiple instruments, multiple teams, and multiple years of observation. Here is what is confirmed. The Kuiper Belt contains 3 chemically distinct populations of medium-sized objects. Those populations are sorted by their formation location in the original solar nebula, sorted so cleanly that 4.5 billion years of planetary migration apparently could not fully erase the record. The dwarf planets form a separate 4th class, geochemically isolated from everything below them. The surfaces of these objects carry no sign of water-rock chemistry. The belt extends far past where the maps said it ended, and the mean orbital plane of the outer belt is tilted in a way the known planets cannot explain. None of that is fabricated. None of it is speculation. The data are in the journals. What it means is that the Kuiper Belt is not the graveyard we assumed, a simple rim of leftover ice at the edge of a well-mapped system. It is an archive, a chemical fossil of the solar system's earliest conditions, preserved in near-perfect cold, in near-perfect isolation, for longer than Earth has had continents. Webb has begun reading it, and the first pages do not describe a solar system that matches the one we thought we understood. Think about where you are sitting right now, and then consider this. The light Webb used to read these surfaces left the sun, traveled for hours, reflected off objects that formed before the Earth existed, and came back to a telescope in space that then sent the data to human beings who have been studying the solar system for a few centuries. And in those first detailed chemical readings, the system is already stranger than the model. The structure is too clean. The water chemistry is missing. The belt is larger than the boundary. The plane is tilted. The James Webb Space Telescope has only read the first page. New Horizons is out there now, past 60 astronomical units, twice as far from the Sun as Pluto was when we first photographed it. Its dust counter is still registering impacts, still measuring a region the maps called empty, still moving through a solar system that turns out to be larger, colder, older, and more structurally complex than anyone fully drew. The graveyard sent something back, not a warning, a record, older than any planet, written in ice and organics, in the dark past beyond Neptune. And the record does not match the story. The edge is not where we put it.